In this video, I want to show you how the delta function can be interpreted in a physical sense. And what I want to do is I want to go back to the harmonic motion example. So we're going to just talk about the simple harmonic motion. Okay, so simple harmonic motion. This was chapter 5. So chapter 5. And so I want to solve the equations. I'm not going to recap any of the material from chapter 5 other than to tell you that we were solving things like mx double prime plus kx equals 0, subject to the initial condition that say x of 0 is 0 and x prime of 0 is some initial velocity, say v0. So what's happening here is, remember, m is the mass of some object, k is a constant depending on the system, and we wanted to come up with a closed solution for x. And we can do this very easily because this is now a second degree linear homogeneous differential equation with constant coefficients. And so we could do this very easily, but what I want to do instead is to do this with the Laplace Transform method, because this will lead us, I'll explain why we want to do this. So what we're going to do is, if we take the Laplace Transform of both sides, we'll get the Laplace Transform of m times x double prime plus kx equals the Laplace Transform of the 0 function. The Laplace Transform of the left side is going to be m times, the Laplace Transform of x double prime will be s squared capital X of s minus s times x prime of 0. Minus s. Oops, I erased too much there. Minus s times x of 0 minus x prime of 0. There we go. So that's the Laplace Transform of x double prime. And then plus k times the Laplace Transform of x. So that's capital X of s. And that's going to be equal to the Laplace Transform of 0, which is 0. And now we'll have the same object. We're going to try and solve for capital X. And what we're going to do, one thing that we can do right away is use the fact that little x of 0 is 0. So this tells us that we're going to have m s squared capital X minus m times x prime of 0, which was v0, plus k times capital X of s is equal to 0. Solving for capital X and moving the mv0 over to the right. So we're going to add mv0, divide by the term that we have in front of capital X, which is ms squared plus k. And this is actually where I want to stop. I'm not looking to actually solve this equation. I just want to show you that we can get to this point with the Laplace Transform method. You could go through and solve this. This is perfectly straightforward. What you would do is you would divide the top and bottom by m. So I'm going to do this in a different color just because I'm not going to finish this. But you could divide the top and bottom by m. So you get s squared plus k over m, and you end up with some sort of a sine curve. Okay, and I'll let you figure out exactly the details there. I'm not worried exactly so much in the answer as I am in this. So this was our example. And what I want to do is I want to compare this to another differential equation. I want to compare this to mx double prime plus kx equals p0 times delta of t, subject to the initial condition that x of 0 is 0 and x prime of 0 is 0. This is almost the same differential equation, except this is no longer homogeneous, and we have different starting conditions, different initial conditions, I should say. If we take the Laplace Transform of both sides, the Laplace Transform of the left is going to be the same. It's going to be m times the quantity s squared capital X of s minus s little x of 0 minus x prime of 0 plus k times capital X of s. P0 is a constant. P0, I should explain, by the way, P0 refers to the initial momentum of the system. And momentum is given by mass times So the momentum here is m times v naught. So it's the mass times the initial velocity. And if we take everything here, we're gonna we notice that x of 0 is 0, x prime of 0 is 0. We're gonna solve for capital X just like we did before. Here we're gonna end up with so here we'll get, let's see, we'll have capital X. So all we have on the left side of our equation is terms that have a capital X in them, right? The other ones are gone. So we can factor out the capital X, and this is going to be P naught over that quantity ms squared plus k. And this is really just, since P naught is our mass times our initial velocity, this is ms squared plus k. So what I really want to show you, what I really want to emphasize here, is that if we look at these steps, we end up with the same Laplace transform, meaning that we'll have the exact same solution to both equations. And so the emphasis here, the real purpose here, is that notice that if we had a homogeneous equation, but we insisted that we have an initial velocity, that means that we're going to give this an initial push, right, with a certain velocity of v naught. That's the same as having initial conditions of our initial position and our initial velocity being 0, but having a non-homogeneous equation. So in a certain sense, this P naught times delta of t can be referred to as our initial impulse. So this is the initial impulse of the system, meaning that we kind of give it a push right at the beginning. And so that's a physical way for this Dirac Delta function to be interpreted. This is often how it's used when you're studying a system and you want to talk about this initial push or this initial impulse.